Hello, we are Group 24. This presentation is about the process that we've gone through to redesign the Vancouver Harbour Ferry to be more efficient. Our team is made up from 5 marine technology students from Plymouth University who are all currently on the MENS programme. We are Nick Williams,
Sam Chown,
Matt King,
Sam Evans,
and Julian Harding.
Our client was asking for a 400-person capacity. It needs to make use of the existing ferry terminals, operate safely with consideration to the crew, passengers and the environment, have a suitable power supply to ensure uninterrupted usage of the ferry, and it needs to be 50% more efficient than the existing ferry and be easy for the current crew to adapt to the new ferry.
The ferry connects the housing of North Vancouver to the business district and shopping areas of West End Vancouver. The ferry will therefore transport a range of people, from businessmen to families, as well as tourists. Therefore, the ferry needs to have the facilities to suit everybody. The ferry runs from 6 a.m. to 1 a.m, so it also needs to have facilities for both night and day operations.
For our research into existing ferries, we looked at 2 different fleets. The first fleet is the Seabus fleet in Vancouver. This is the fleet our ferry will join and replace. The Seabus fleet is made up of 3 ferries. Each ferry has a capacity of 385 passengers, and it makes its 3.24 kilometre journey over the harbour in approximately 10 minutes. This allows it to operate a 15-minute schedule. The ferries make up to 50 crossings a day with an average cruising speed of 11.5 knots. All of the Seabus fleet's ferries are made up of an aluminium catamaran hull and are double-ended, so there's no need to turn around in the dock. The Seabus fleet currently operates using 4 diesel engines. Each one is used to power its own propeller. The second fleet we've researched is the Red Jet fleet, which carries passengers from Southampton to the Isle of Wight. These are an example of a high-speed ferry with an average cruising speed of 33.5 knots. The capacity of the ferries in the Red Jet fleet are between 180 to 190 passengers, making it a lot smaller than our required capacity. Just like the Seabus, the vessels are made from an aluminium alloy hull in the style of a catamaran. To achieve the high speed, the ferries use 2 diesel power engines powering 2 Chimera water jets which propel it across the water.
power output. We have to think about how much power the source gives and whether it is enough to power what we need. Reliability. The ferry needs to be able to function day in, day out without the need for extended maintenance periods where it can't function. Size. The power source can't take up so much room that there isn't enough space for all the passengers. Efficiency. The power source needs to be efficient enough so that it doesn't cost too much money or weight to weigh the ferry down with its fuel. Emissions. We need to think about how the power source's emissions affect the local environment. Photovoltaic cells. The idea is to mount photovoltaic cells over all unused sections of the deck of the ferry to generate electricity from the sun. Although the energy generated is carbon neutral, not enough is produced to run the ship's motors. Also, they aren't reliable as they depend on the weather. Sail. Mount a wing on top of the ferry and use it when it's windy to reduce the fuel used by the motor. It's a very green source of energy, but again it isn't reliable as it depends on the weather. Hydrogen. Use hydrogen fuel cells to generate electricity and power a motor. There are no harmful emissions produced when running, only water, though this would require the storage of hydrogen, which is very volatile.
Nuclear power could give us a very good power output of more than 50 times what was needed, but due to its size, weight and the nuclear waste produced, it did not score so highly. Natural gas and diesel generators were quite similar, as they both gave the required power output and were of good weight and size. They're also a stable choice as they are unlikely to fail whilst in use, but natural gas generator was a less viable option as it is harder to safely store natural gas on board a ferry.
Our solution is to use a diesel generator running a biodiesel mix as the main power source and generate all the power needed for propulsion, and use a wing mounted on top of the ferry to reduce fuel consumption when it's windy. Also, we are going to mount solar panels around the unused faces of the ferry to charge a battery bank, which in turn powers all internal electronics. The diesel generator can be used to charge these if the weather doesn't allow for it.
We made a table of suitable diesel generators with their power outputs, and we calculated how much fuel they would use to produce 1 kilowatt hour of energy, and made a choice of the most efficient generator, which is the Cummins DQD-AA.
When looking at propulsion, we had a number of considerations. Efficiency is our main priority. The vessel also has to be manoeuvrable and have low noise and vibration so comfort for passengers isn't compromised. The propulsion method had to have a power requirement below 560 kilowatts and reach 13 knots, but also be easy to maintain. We considered a number of propulsion methods, including contra-rotating propellers. These reduce noise and reach a high speed, but do not give added manoeuvrability. Water jets are inefficient at low speeds below 15 knots, but are manoeuvrable and reach a higher speed. The voice Schneider or cycloidal drive gives added manoeuvrability and is efficient. Rim-driven propellers have only one moving part, so noise is hugely reduced. However, this is a relatively new method of propulsion, so the speeds reached are not great enough. Azipods require too much power for our vessel, and azimuth propellers add manoeuvrability but are difficult to maintain. Our choice was the Voith Schneider propeller, as it is the best all-rounder. It is used on passenger ferries already, including the red funnel.
There are a number of key requirements when considering what material to use for the vessel in terms of both structure and long-term economics. Due to the design specification, weight needs to be kept to a minimum while still having the durability to cope with the impacts of regular docking. The current vessel has been in operation for 38 years, so the materials chosen will need to last just as long, but with as little maintenance as possible. The impact that the vessel will have over its lifetime is also a consideration, particularly if repairs require unplanned quantities of material. A number of materials were eliminated due to impracticality or unsuitability. The remaining materials, steel, aluminium, composites and wood, have been scored against the table of requirements. Out of choice, we would have constructed the vessel from composites. However, saltwater ingress can cause catastrophic structural failure. As a result of this, the most suitable material is deemed to be aluminium, and this is what we shall use for the hulls and lower sections of the boat. This is due to its high durability, low weight and low cost. After considering the implications, we have chosen to make the upper cabin area from composite material. This is to allow the boat to be lighter, as well as requiring less internal bracing, and also providing a solid support for the mast.
We have chosen to use a catamaran hull over the single hull design as it will provide better stability, meaning more comfort for the passengers. The triple hull design is not necessary for our passenger ferry, as it will not benefit any more and will only increase the cost.
Hull resistance compromises 70% of the total resistance a vessel encounters when it moves through the water. Therefore, less resistance, the less power required, improving fuel efficiency and reducing emissions. The product we have chosen to use is ALFC by Nippon Paint. This gives a 10% reduction in fuel consumption and stops debris building up.
Our final design is a dual-deck catamaran incorporating the ideas specified earlier. Aerodynamics were considered early on in the design, as well as the shape of the hulls. These have been designed not only for planing, but for use without a rudder. Front and rear decks will have built-in solar panels, as will some of the roof space, depending on the power required. As a rough guide, dark blue areas will be aluminium and yellow areas will be composite. Light blue areas denote transparent. The exception to this is the front deck and bow tips, which will be of a mixture of the two. The vessel is single directional, as the manoeuvrability of the propellers allows for quicker turning. Therefore, the view from the bridge is primarily forward and sideways, as the area around the docks is free from obstructions, so rear windows will be limited. Cameras will be fitted to offer better view of all angles. Main access for passengers will be from the lower deck through train-style sliding doors.
The next stage of the project is to produce a physical 3D model and a written report. Thank you for listening.